so optimization is basically just min-max word problems. Okay, so we know how to find mins and maxes. Okay, we're just going to turn these into word problems now. So you have two sheets in front of you. One of them is a list of steps for optimization problems. The other is some practice problems that we're going to do together here. So we're just going to kind of jump into the first example here, and we'll go through the steps together for this first example. Okay, the first example is pretty straightforward. Okay, it's not like a true word problem. All right, so most of the time, these problems are going to be geometric in nature. Okay, there'll be some kind of geometric picture to draw, kind of like what we did with related rates. This one, there isn't really any picture to draw, though. We just want to find two positive numbers such that the sum of the first and twice the second is 64, and whose product is a maximum. There's no picture to draw for that, so we can kind of skip the first step. Okay, then the second step is to find the objective function. Okay, objective function just means what do we want to maximize or minimize. Okay, well here it says we want to find the product that's the maximum. So I'm taking two numbers. Okay, now I can just denote those x and y. So I can say x is the first number, y is the second number. So then my equation, okay, that I want to maximize, we're going to call this the objective function, is just the product of those, x, y. Okay? Now, I can set this equal to whatever I want. Right? I can call this m for max, okay, whatever. That we don't have a number that's going to be equal to. Less. Okay? So now it says identify the constraints. Okay? If your objective function has more than one variable, we'll need to use constraints. Most of the time, what that looks like is writing a second equation. Okay, well, we're given a little more information here. We're told that these numbers, okay, the sum of the first and twice the second is 64. How can I turn that into an equation? Yeah, x plus 2y equals 64. Now, the fourth step says reduce the objective function to one variable. Okay? I don't want to have two variables in my objective function. Okay? We're going to eventually take the derivative here. So I want this to only be in terms of one variable. The easiest way to do that is to take my constraint, okay, my second equation here, solve it for one variable, and then plug that into this equation. Okay? It doesn't matter which variable we solve for. Okay? So a lot of times there will be one that's easier to solve for. So which one do we want to solve for in this equation? X. Right? All I would have to do is subtract 2y over and get x equals 64 minus 2y. So now I can take this and plug it in place of x in my objective function. So we'll have 64 minus 2y times y equals whatever equals m for max. What's it? So, I mean, we can multiply this out. Okay, that'll probably make it easier to take the derivative of. So we just get 64y minus 2y squared. So now I have an objective function in just one variable. My goal is to find the maximum of this. Okay, we know how to do that. Okay, that's what we've spent the last few weeks on. Okay. So what are my steps then to find the maximum value? Take the derivative, right? So I'll come up here and we'll say m prime is do 64 minus 4y. So yeah, I was just gonna mention that. So here, we're not thinking about y as its own function. We just randomly assigned x and y as these two variables. So we're not doing implicit differentiation here, right? We're thinking about x and y as just both independent variables, right? So now, once I have my derivative, how do I find a maximum?
Zeros.
Oh, I skipped a step. Sorry, I did skip a step. Let's back it up one step. So I went straight from 4 to 6. So I skipped the identifying the domain part. Okay, this is an important part. So we need to use the context of the problem to figure out any domain restrictions. Sometimes there won't be any domain restrictions, but here there would be. Okay, so I know that x and y first are both positive numbers. So right off the bat, I can say that x and y both have to be greater than 0, right? So say x, oh wait a second before I write it. So I know they both have to be greater than 0. And then I also know that their sum, okay, the first and twice the second is 64. So can I make any upper bound out of that? What's the highest either one of them could be? Yeah, right? So I know that both of them have to be between 0 and 64, right? So, I mean, that's all we're doing when we are jotting down our domain, our constraints. We're just kind of looking at the problem and saying, well, if they're positive, it has to be greater than 0. And, well, their sum is 64. The sum of the first and twice the second is 64. So I know that neither one of them can be bigger than 64. Well, if they're both positive, then no. Because one of them would have to be at least 0.00001. And so the other one would have to be less than 64. Okay? A lot of the time, we will be working with real-world problems, meaning that in most of the problems we do, our variables will have to be at least greater than 0. Okay? Sometimes we'll then be able to find an upper bound, sometimes we won't. Okay? But most of the time, they'll be greater than 0. Okay, so now let's jump back in and say, we found our derivative, so now how do I find a maximum? Set it equal to 0. Yeah. So this is pretty easy to solve, right? I would just add the 4y over, divide by 4, and we get y equals 16. Right, so this is a critical point, right? We have no idea if that's a min or a max. So what we want to do is put this on a sign chart. So I'm going to take a value less than 16 and then a value greater than 16 and plug it into my derivative.
1.
Sure, let's say 1. So if I plug 1 in here, I get 64 minus 4. Positive. If I take a value greater than 16, it's going to be negative. So at 16, do I have a min or a max? A max. Right? So that is what we're looking for. So we're good. Okay? That's only half the answer, though. How do I get the second number? Yeah, just plug it in. Right? So where should I plug it in? So I want to plug it in somewhere that the only thing I'm solving for then is x. Right? If I plug it into this one, I still have 2 unknowns. I still don't know x or m. But if I plug it into this one, I would only have one unknown. Right? The only unknown then would be x. Okay, so once we have half of our answer, we would want to plug it into this one, the constraint equation. So if I do that, x plus 2 times 16, x plus 32, so x equals 32. Now, in this equation, or in this problem, I should say, the domain didn't really come into play. Okay? We didn't get any negative possibilities. The one critical point we got was a maximum. So our domain didn't really come into play. There will be some problems, however, where we may get a negative answer here. Okay? We may get a negative critical point, and we would be able to throw that out immediately because we know everything has to be greater than 0. We'll also take a look at a couple of problems where so let's say this critical point we got was a min, and we were looking for a maximum. In that case, we would have to use our endpoints. Okay, and we'll look at those examples here in a second. Okay. But we feel okay with this one so far. Okay. It's just a max min word problem, okay, where most of the time we'll be writing 2 equations, solving one of the equations for one of the variables, plugging that into the equation we want to maximize or minimize, taking the derivative, setting it equal to 0, finding critical points, testing whether that's a min or a max, and then using that answer to find the second piece. Okay. Questions? 59.
I was trying to see it on your phone and on the exam schedule.
All right, so let's try this second example here. Okay, this one's a little bit more of a word problem. So we've got a farmer. He's going to fence in a rectangular pasture adjacent to a river. The pasture has to contain 180,000 square meters to provide enough grass for the herd. We want to figure out the dimensions that would require the least amount of fencing. Right? So here we can start by drawing a picture. Okay, what? We got a river. Adjacent means next to.
And then we don't need fencing on like by the river. So.
All right. So this fence is just going to have 3 sides. Right? The 4th side is the river itself. So let's take a look at what we know. Okay, the only actual piece of information that we're given is that the area of this pasture has to be 180,000 square meters. So I don't know the dimensions of this at all. Okay, that's what we're going to try to solve for. So, well, yes, but first, let's assign some variables. Right, so we could call these sides x and this side y. Okay, or, you can use whatever variables you want.
I was going to use M and C because Tab was moved.
That works. All right, so now let's first write our objective equation. Okay, what am I trying to maximize or minimize?
Minimize the amount of fence.
Minimize the amount of fence. So how can I write an equation for the amount of fence?
2m.
Yeah. So I can say it's going to be.
Oh, sorry, you're not using m.
2x plus y. Right? And again, we can set that equal to whatever we want. Okay, I'll set it equal to f for fence. So now we need to use the other piece of information we had. Pasture must contain 180,000 square meters. How can I write that as an equation? Set what equal to 180,000? Yeah, this is just the area, right? So the area of a rectangle is just x times y. So we'll say xy equals 180,000. So now what?
You can take the first equation and get it one of the variables.
So the one that I want to solve for one of the variables is going to be this one. Okay, it has to be this one. Yeah, so we're going to divide by x or y. Now, why does it have to be this equation that I solve for one of the variables?
Because
Yeah, because this is the one that I want to minimize. Okay, so I'm going to be taking the derivative of this one. So I want to get this one in terms of one variable. So I need to solve the second equation here for one of the variables. Okay, let's solve for y. So if I solve for y, just divide by x. Right? So we get 180,000 divided by x. So now I'll take that and plug that into this equation. So we will get 2x plus, now since I'm going to take the derivative of this, I'm going to write this as 180,000 times x to the negative first. Okay? So 2x plus 180,000 times x to the negative first equals f. Now what? Yeah, so we have our objective function in terms of just one variable now. And now I can take the derivative.
Wait, so
Yeah, this is just one term. Yeah. Yep. Okay. So now what?
equals 0.
Set it equal to 0. Now, again, when we're taking the derivative, it's easier to think about negative exponents. When we're actually solving an equation, I think it's easier to now bring this back to the denominator and say this will be 180,000 divided by x squared. Right, so yeah, if I take one of these to the other side, I would just end up with 2 equals 180,000 over x squared. So now the reason I think it's easier to think about this as over x squared instead of times x to the negative second, we can cross multiply now. Right? So if I cross multiply, I would just have 2x squared equals 180,000. Divide by 2. Square root. So what's the square root of 90,000?
It's something with a 3.
What is it?
I just heard
It's definitely 300, yes. Now, technically, we would get plus or minus 300, right? But, right, negative 300 doesn't make sense here because we can't have a length of negative 300. So, yeah, we forgot to do the domain, didn't we?
Yeah, I didn't want to interrupt you while you were writing stuff. I'm like,
no on a test will we have to put the domain on there, or as long as you know the domain will put anything that doesn't.
As long as you understand that, this can't be negative 300. We'll look at examples where the domain is actually pretty important. But for this one, we just know that we can't have negative 300. That's not super important here. So we do need to test, though, to make sure this is a minimum value, right? We're looking for a minimum here. So let's put this on a sign chart. And plug in a value less than 300, a value greater than 300.
1.
Plug in 1. So 2 minus 180,000 over 1. Negative. 2 minus 180,000 over 180,000.
Did you say 100?
Yeah. Positive, right? So, yeah, it's a min. If we're changing from decreasing to increasing, that would be a min. So that's what we want. So we're good. So again, that's only half the answer. How do I find the other half? Plug it in where?
That one. The X. Yeah, that one too.
Yeah, we want to plug it into one of these, right? So that I only have one variable remaining. So we actually already have this solved for y, right? So I can just say y equals 180,000 divided by 300. So what do we get? 600. All right. So my dimensions, my final answer here that would require the least amount of fencing is a 300 by 600 pasture. That's the answer. Okay, and we may want to write out a half a sentence just saying the dimensions that would require the least amount of fencing are 300 by 600. Right, so we do want to make sure that we answer the question. Okay, sometimes the question will ask us, something straightforward like this: what's the least amount of fencing? So we will get into some where we'll look at cost. Okay, how do we minimize cost? And then, we'll have to find, we find this fencing, but then we'll also have to answer what would the actual cost be. Okay, we just have to look at the question to make sure we're actually answering it. All right? Questions? All right, let's try to squeeze one more example in here.
I know there's some guys.
Yeah, open boxes being constructed from a small piece of sheet metal. Inches by 3.
I said no. All right.
Either way, we're probably going to have to do it.
This is not a democracy. This is a dictatorship. All right, so we've got an open box being constructed from a piece of sheet metal. The sheet metal is 18 by 30, and what I want to do is cut out the corners, cut out squares of equal size, so that I can fold it up and create a box. I want to figure out how big to cut those squares out to create a box of maximum volume. So this is a picture of what we're doing, right?
Okay, come on. We have 4 minutes left.
You have this on your sheet. Right? You've got your piece of sheet metal. There's a rectangle on there, isn't there?
Oh,
yeah. So this is what we're doing. We're taking this rectangle, cutting out these corners so that I can fold up the sides and create a box. My goal is to figure out how to create the box of maximum volume. What I know,
The thing is, I would never read that and know what to do.
wait, why wouldn't you know what to do?
Like, I would never read that, and it would be like, what size square should you cut out? And I would be like, what are you talking about? I would not have heard. Like, unless they showed me that specific visual, no way.
Okay, well now you have seen that visual.
Yeah, but no, they're not going to ask that.
This is a very common question, like creating a box of maximum volume. This is actually like a really
Do they
common.
show us that?
No.
We're not that lucky.
We're going to get
But
so
yes.
far into the year, and then we're going to have forgotten
So what I know is that this piece of sheet metal is 18 by 30, right? I don't know how big to cut out these squares. Let's call that measurement x, right? So everywhere, this is going to be the same.
Oh, yeah.
It might be a good idea to draw this. So
Don't laugh at me.
if I think about cutting out these boxes and folding this up, this will be the new length of one side of my box. How can I express this length here?
L.
30
30 minus 2x. Right? So I can say that, I'll write it here, this side here, just from here to here is 30 minus 2x. How about this piece here? 18 minus 2x. So what I want to do is maximize the volume. So what will the volume of this box be? Exactly. So when I fold up these sides, this will become the height, right? So this length is x. You see that? All right. So
Stop.